Hello, so in this video we're going to go through Hess's Law and look at some of the calculations using the theory of Hess's Law. Hopefully before watching this video you've watched my Hess Law experiment video because that should help this make more sense. However, this should still make sense without having to watch that video. So the purpose of this video is to make sure that you can state the definition of Hess's Law and then use Hess's Law to calculate the enthalpy change of a given reaction. So, Hess's Law is a law that states that the enthalpy change for a chemical reaction is independent of the route that is taken. So what that means is that the enthalpy change for an overall reaction from start to finish will be identical if you take 1 step, 2 steps, 3 steps, 4 steps, however many steps you want to get there. Doesn't matter, as long as you're starting in the same place and finishing in the same place, it should have the overall enthalpy change as the same. So, if we take an example of a neutralization reaction between sodium carbonate and ethanoic acid. So, this is a neutralization reaction, and one way we can do it in 1 step is by adding the solid sodium carbonate into the ethanoic acid and neutralizing it that way. Okay, so we're going to call that experiment A. We could, however, if we wanted to, do it in 2 steps where we make a solution out of the sodium carbonate first, so that's shown in this equation here, reaction B, and then use that sodium carbonate solution that we've made to then neutralize the acid in what we're calling reaction C. So the 2-step process obviously takes more time, and you may wonder why you would bother doing it that way. Most people would probably just do it in 1 step, but this is one way that we can use to help prove Hess's law. So, if Hess's law is true, then the enthalpy change that we get from reaction A should be the same as the enthalpy change for B plus C, because we are starting with the same things and finishing with the same things. We're just doing it in different numbers of steps. So, from looking at the equations as they are, you might struggle to see how that all fits in, but I'm going to show you on the next slide how it works. But from the experiment that I did in my kitchen, since we're not allowed in school at the moment, these were the results I got from the kitchen experiment we did, and we did find in that experiment that the enthalpy change for B and C added together did give you the enthalpy change of A, which means that Hess's law must be true. He wasn't just making it up. So the way this works, which should hopefully help you see how it all ties in together. So usually when you're given a Hess's law calculation, you're given what's known as a target equation. Okay, so this here is our target equation, one with the green box around it. Okay, this is the reaction we're really actually interested in. The reason we would use Hess's law usually is because there's we're trying to find enthalpy change for a reaction that's not very easy to do. So what we can do is use easier reactions that end up making that thing in different numbers of steps to work out what the enthalpy change would be. So let's just say reaction A was too difficult to do in the lab, which is clearly not because I managed to do it in my kitchen, but just for the sake of this learning experience. What we can do instead is use the information we know from B and C to work out what the enthalpy change for A would be. Now, the way you can see how this ties together is if we go through everything in the target equation and identify where it is in the reactions below. So the sodium carbonate solid, that's here. Okay, we've then got, which is in colour, this ethanoic acid solution. So that's down here. And the equation's down below. And then the next thing in the target equation we've got is our sodium ethanoate salt, which is down here. And then lastly, we've got water. So that's in more than one. So I'm actually going to ignore it for now. And then we've got carbon dioxide, which is only in this one here. I'll just highlight the water detail. Okay, so you will see that there are some things that are not in the target equation, And this is the bit that I quite like to do, because this is the point where you cancel things down that are repeated. So, for example, you can only cancel down on a diagonal. So we've got a sodium carbonate over here that can cancel out with the sodium carbonate over here. So it has to be on the separate sides of the reaction arrow. Okay, so 1 mole of that and 1 mole of that can cancel out. We then have 1 mole of water that can cancel with 1 mole of water. There's not another mole of water to cancel this one out, so we're just going to leave that one. So that stays there. And then other than that, there's nothing else we can cancel out. So if we then rewrite everything we've got left as one equation, so we've got the sodium carbonate, then we've got this ethylenic acid, and then we've got the sodium phenolate salt, and then we've got 1 mole of water and 1 mole of carbon dioxide. And what you should notice is what I've just written is identical to what our target equation was. So that is the reason that when you add the enthalpy changes for B and C together, you end up with enthalpy change of A, because when you cancel everything down, it's duplicated on both sides of the reactions, then you end up with that target equation. So if we hadn't done reaction A in the experiment, we could work it out by doing delta HB plus delta HC, which would give us the 9.30 plus positive 2.22. Positive and negative signs are important with enthalpy calculations, which would mean that the overall enthalpy change would be 11.52 kilojoules per mole. Okay, so that's how it works. If we go to the next slide, so we're going to go through this example now for a different reaction, and this one is going to require us to actually manipulate the reaction equation slightly. So if we go through the target equation and look for the things we need down in the 2 equations we're given below. So the solid carbon is here. Now you will find that they don't always have the same number of moles, which is fine, because we're going to take that into account afterwards. We've then got oxygen. However, the oxygen appears in 2 equations, so you're actually going to pay less attention to that until after we've manipulated the equations, which will make sense in a minute. And then carbon monoxide, CO, is over here. Okay, so if I number these reactions 1 and 2, and we're going to look to see how we need to manipulate them to get our target equation. So for the carbon solid, we need 2 moles of that, which means we're going to have to times this equation by 2. And then the oxygen appears in both of them, so we're just going to skip that and go over to see how we can get our 2 moles of carbon monoxide. So there's 1 mole of carbon monoxide here, so we would need to times it by 2 to get 2 moles. But also the carbon monoxide's on the wrong side of the reaction, it needs to be a product, and at the moment it's a reactant, so what we need to do is reverse that equation. If we then write out the equations again with our manipulations, so we've got 2 moles of solid carbon this time, and then 2 moles of oxygen. Everything needs to be multiplied by 2, not just the thing in your target equation. I'm going to put this 3 there by accident. Okay, so you have to multiply everything by 2. That's reaction 1. Then reaction 2, we're reversing it, so I'm going to reverse it first. That makes it a bit less confusing. So you just write it back to front. Carbon dioxide goes first, then you carbon monoxide plus half a mole of oxygen. And then we need to multiply it by 2. So we put 2 input there, 2 input there, and 2 times a half is a whole, so we can just take that one away. Now we get to the fun part, the tidying up part, where we cancel things down. So if you go to the top equation, this is probably the easiest way to do it, and just look to see what you have on the left and see if you can cancel in with anything on the right. So 2 moles of solid carbon. There's no solid carbon on the product side at all. I'll draw a line in here just to cancel with, so we can't cancel that down. 2 moles of oxygen. Well, there's 1 mole of oxygen over here, so that means we can take 1 of those moles of oxygen away. Okay. And then we've got 2 moles of carbon dioxide, and then there's 2 moles of carbon dioxide on the other side as well, so they can cancel. And then all we've got left is that carbon dioxide, and there's nothing to cancel that with. Then, if we rewrite what we've got left as one whole equation, we've got 2CS plus O2 gas, giving us 2CO gas, which is our target equation. So that means that we've manipulated them properly. So now what we have to do is manipulate the entropies to match. So for number 1, we were multiplying it by 2. So we do the same. So we multiplied the reaction by 2, so we do the same with the entropy change. So that would give us 1,500 and minus 1,574 kilojoules. And then for the second reaction, we're multiplying it by 2, so that's 566 times 2. But because we reversed it, it's not a negative anymore, it's actually a positive. Okay, so if you reverse the reaction, the number is the same, the energy change is the same numerically, but it comes off the sign. So now all we have to do is take the net of these two, so it would be minus 1574 plus 1132, which gives us 1574 plus 1132 minus 442 kilojoules. Okay, so that's the first example. Just remember when you're doing entropy calculations, you always put a positive or a negative on your final answer, depending on what it is. So that means it's an exothermic reaction because it's losing energy. Move on to the next example. So we've got CH4. Laser. CH4 here. If we look for it down in our smaller equations below, that's here and it's nowhere else. O2, that's here and here. So because that's in more than one reaction, we're probably going to ignore it until the end, just to make our lives easier. CO2 as a gas, that's just here. And then water as a liquid, that's here. Right, so that's just got everything in our target equation. So now if we go through to here, we're going to manipulate them. So the CH4, we've got the right number of moles, however it's on the wrong side, so we're going to need to reverse this reaction. Okay, so that the methane is actually a reactant and not a product. Then oxygen we're skipping because it's in more than one equation. Carbon dioxide, we've got the right number of moles and it's on the correct side of the reaction, so that doesn't need to change. And then for the water, we need 2 moles, so we'll times by 2, but it's on the correct side of the reaction because it's being produced, so we don't need to reverse it, right? So if we rewrite the equations, just make sure we've got our target one. So the first reaction we need to reverse, so that means CH4 comes first. And then it's the carbon solid plus 2 hydrogen gas. And then the middle one we didn't need to change, so we're just going to copy that down again as it is. And then the third one we had to multiply by 2. We didn't need to reverse it or anything. Just remember 2 times a half is a whole. Okay, so then if you do the cancelling down, so the CH4, there's nothing to cancel with on the other side. Carbon solid in 1 mole and 1 mole, so they can cancel down. 2H2, there's a 2H2 down this bottom left as well, so they can cancel. And then we've got O2, O2, they can't cancel. CO2, there's nothing to cancel with that. And then nothing to cancel with water, so we write everything we've got left. Those 2 moles of water can be added together. 2O2, and then CO2 gas plus 2H2. And that says now got our target equation. Now we need to do is change the energy. So if we reverse the first one, that means it becomes positive 74.8, Middle one didn't change, so that's still negative 393.50. And the last one was multiplied by 2, so it's still going to be a negative. I'm not reversed it. And then the numerical value of it is going to be 571.66. So then if we take the net sum of all of these, that means it's 74.8 minus, or plus minus, which becomes a minus, 393.5 plus negative, so take away 571.66. Which means that the overall value is negative 890.36. Okay, so that's the overall energy change for that target equation up there. Okay, next example. We'll go through the target equation again. So N2, it's like a treasure hunt, isn't it? And O2, some lots of them. Then we've got N2O5, which is down here. So let's do our manipulating. So number one doesn't have anything other than oxygen in it, which is not really helpful because oxygen's in another thing. So we're just going to leave that for now. The N2, we need 2 moles of it, so that means we're going to have to multiply the second reaction by 2. So we don't need to reverse it because it's on the correct side, we'll have to multiply it by 2 to get 2 moles. The next thing, the target equation is the N2O5, so we need 2 moles of that, so we're going to have to multiply that by 2, and it needs to be on the other side of the reaction, so we're going to have to reverse it as well. Okay? So because we don't know what to do with number 1 yet, that means it's probably there to cancel other things down. So what we're going to do is write down the manipulated equations 2 and 3, and then check back for equation 1 to see how we need to modify that one. So for reaction 2, we're multiplying it by 2. 2N2 gas plus 6O2. Remember, don't forget to multiply everything in the reaction. And then that will be 4 HNO3. Okay, then number 3, we're reversing it, so I'll write it first. State symbols are important here, but if you're writing them down, you don't need to. As long as you remember if things are doing as gases. And then we need to multiply by 2, so that becomes a 4, that becomes a 2, and that becomes a 2. So for the cancelling situation then, the target equation, or the equation 1 that's left, the thing that's in it that we really need is hydrogen and water, because oxygen's in different things, it's usually best to for that. So if we look at how much hydrogen and how much water we need, we need 2 moles of each, and this reaction has 1 mole of each, which means that for the cancelling purposes, we're going to need 2 moles. There's no hydrogen and water in our target equation, so they must need to be cancelled out. However, if we were going to write that out in that respect, so let's do H2, and so then that's a whole oxygen, and then 2H2O. They are not actually on the correct side to be able to cancel, so that means we must need to reverse that reaction as well. Okay. So, erase all that. that first one, so we need to multiply it by 2 and reverse it. We've got 2H2O then into 2H2 gas plus O2 gas. Right, so I'm just going to remove these red boxes now to make it a little less messy. So if we just check that we've actually got our target equation now, so we can cancel these 2 waters with these 2 waters, these 2 hydrogens, these 2 hydrogens. Then for the oxygen, we've got 1 on the right hand side altogether, and then 6 on the left hand side altogether, so that means that'll cancel to give 5 moles there. And then we've got 4 HNO3 and 4 HNO3, and that's the only things we can cancel. So we just write what we've got left, 2N2 the gas plus 5O2 the gas into 2N2O5 as a gas, and that's it, which is our target equation. So now we know we've manipulated all the equations properly, we can then manipulate the energies. So for reaction 1, that's going to become positive, and 285.8 times 2, so positive 571.6. Then the middle one we just need to multiply by 2, so that's still going to be negative 348.2 times 2, 696.4. And then the last one we reversed it to become positive, and we're also multiplying by 2. So that becomes 153.2. Then if we take the sum of all those, so that'll be 571.6 plus minus, so take away 696.4 plus 153.2. That gives us positive 28.4 kilojoules. Okay, so that one's a bit harder because of the equation that was just really there for cancelling purposes. So now there's a few for you to try yourself, and there's answers at the end. My advice would be to lay out the working as I've shown you in the examples, and check that you end up with your target equation before you then change the energies. So you can pause the video as required to work through these, and then you can check your answers at the end. Okay, so hopefully after watching that video you can now state the definition of Hess's law and also calculate the enthalpy change for a given reaction using the theory of Hess's law. And I'll show you the answers now. Okay, I hope you found that video helpful. Feel free to like and subscribe, and I've also got another video on Hess's law using cycle diagrams that you may want to watch as well. Thank you.